Okay, welcome everybody. Monday, 5 p.m. Is everybody able to hear me okay? Alright, it's 2, 3, okay, perfect. Okay, so let's complete the last section of this chapter. 2 parts, first circular motion, second drag force. Let's go with circular motion, which was one of the lectures that was optional on Kinematic 2D. So let's revisit this. What do we need to know? Let's update our note and summarize the essential concepts of circular motion. I'm going to write circular motion as CM, and I'm going to add a U in front of it for now. So this means we're going to investigate the concept of uniform circular motion. The uniform refers to the speed, and it pretty much says that the speed is constant. So as you've seen already, you know that the velocity will change as a function of time, obviously. If we're going in a circle, circular motion, we're doing this. At any time or any place on the motion, if we plot the velocity vector, it will always be tangential. And this is true because we're dealing with a circle. If you deal with an ellipse, that won't be true. The velocity will not be always tangential. Uniform means that the speed is going to be the same, which means that the magnitude of the velocity will stay the same, which means that if you're going at 5 meters per second at this particular position, you will keep going at the same speed forever and ever and ever around the center. So let's call the center R. The interesting thing about circular motion is now as we try to identify, okay, so if the velocity is tangential and the velocity is constant, can there be an acceleration vector in the same direction as the velocity based on what we know about kinematic? Yes or no? Excellent. Cannot be, otherwise the velocity will change. But we're dealing with uniform. And yet, even though the magnitude doesn't change, obviously the velocity of the vector, the direction of the velocity vector do change. Hence, there's still got to be an acceleration somewhere, somehow, that even though it doesn't change the magnitude, therefore it cannot be collinear to my vector v, but it does change its direction. If it's not parallel to the v vector, what is the other option that is available to us about the direction of the acceleration? If it cannot be parallel, what is the only other option? Yeah, perpendicular. Excellent. Which means we have 2 cases. It has to be along this line. This is the one that will change the direction of the velocity without changing the magnitude. And so therefore we have 2 options. Either it's out or it's in. We're going to deal with the centripetal acceleration, strictly centripetal, and stay away from the centrifugal. And hence, we're going to consider the acceleration inward. So at any time, A is radial, and at any time, A is towards the center. And since A is perpendicular to V, A will have the effect of changing the direction only. So it's a change of direction, not a change of magnitude. So that's all we need to remember about a motion that happens to be circular instead of a translation like we've done in chapter 2 and chapter 4, or 3 and 4, sorry, or whatever, kinematic vector. In this particular case, the acceleration is not parallel to the velocity, but it's entirely radial, and this is the one that will cause the direction of the velocity to change. All right, so we know the relationship between their respective direction. What about their magnitude? Well, there's still a correlation between both magnitude. This correlation is very easy. It can be written in scalar quantity or scalar form as this. As we're going to see as we start the energy chapter on Wednesday, this will be a dot product. Now we will revisit from chapter 2 on vector on Wednesday. So it's nice because this is a constant. If it's a uniform circular motion, magnitude of V is a constant. Therefore, A is a constant. And we can always relate the two together, which is nice. That's it. That's what we need to know about uniform circular motion. Now, if you're dealing with a case that is not uniform, but still a circular motion, then the general case would be everything is the same. V is tangential. But now if we're dealing with a circular motion, where possibly a case where you're still going in a motion, you still maintain that distance r with respect to the circle, the center of the circle. So this doesn't change. Or it's still a constant. But you're going to rotate either faster and faster and faster and faster, or slower and slower and slower and slower. Obviously, if the velocity magnitude start to change, then there must be an acceleration in that direction. If A, and I'm going to call it tangential, is in the same direction as V, then as V go in a circle, and the reason why V goes in a circle is because of the radial component of A, which I will call AR, radial. AR, same as before, is responsible for the circular motion. AT, which is tangential, and therefore parallel to the velocity V, will cause the magnitude of the velocity to change. If it's in the same direction as this case, then V will speed up in magnitude. If AT is in the opposite direction, then obviously V will slow down. Which means that for circular motion, which is not being specified to be uniform, the overall acceleration vector is not towards the center. The radial component will cause and will be responsible for the circular type of motion, and the tangential will be responsible for changing the magnitude of the speed. However, even in this case, the relationship between those two still holds. Okay? Okay, so now let's imagine that we have, let's use a basic example. You are playing with how does that work? Those little kids who have a string, and it's like a lasso. So they're going in a circle like this, parallel to the plane, and with whatever object on the string. I don't know how to call this. So if you look at from the side, this is our circular motion perpendicular to the plane, and then there's a tension hold up right here. So of course the velocity is into the plane. Since the circular motion is in purple, then the acceleration vector is along this. The acceleration vector is not along here. You always have to identify where's the center of your circle. In this case, it's right here. Therefore, the acceleration must always be towards the circle, the center, a radial. Common mistake is to put it along the string. Okay, so really, the only component of the string that will contribute to the acceleration, if this is alpha, it's going to be t cosine alpha. This is the only one that will contribute to the radial acceleration. And the radial acceleration is the one that is equal to v squared over r. Okay? If you add the weight here, then the y component is going to be the one that is equal to the weight. Okay, so this one contributes to keeping this rotational motion at the same angle theta and the same height. But the radial component of the tension along this axis, along the radial acceleration, will be the one that creates that acceleration and that circular motion. Okay? So now we see another way, as we do Newton and obtain the left-hand side with the net force, we have another way to relate the acceleration with its cousin kinematic variables, the velocity. Okay? Questions on this? So, if you look dealing with a planetary system, if you have the Sun here and the Earth here, obviously, if we consider and we ignore Kepler, and we make our life easy by considering that it's a circle, very close anyway, is close to zero, then the centripetal acceleration is still going to be towards the center, and the velocity is going to be tangential. Since the velocity is the distance over time, if you take the distance traveled, in this case that's the circumference of the circle, 2 pi r, then this time becomes the period. Therefore, if you know the distance between the Earth and the Sun, and you know its actual linear velocity, then you can predict the number of seconds that the Earth will take to go around the Sun. And in this case, it will be 365 days that you can convert back into seconds. Or you can go the other way around. If you know the period, which is something we can observe, set up a laser that bounces back, or find other ways to figure out the distance between the Earth and the Sun, bang, you can deduce the linear velocity of the Earth, approximately, because we assume that it's a circular motion. Okay, so that's what summarizes circular motion. There is not that many problems for this concept. It will come back to us in energy and as we do gravity, but it's very simple relationship. So the type of questions are rather boring. So that's why there's not that many on the course website. Okay. The only interesting application that we have are twofolds. First, band curved and vertical loop. Let's start with the vertical loop because since band curve is already on the lectures, you've seen them, we can just go fast on them. Loop is not there. So let's imagine that you have a system that goes down the ramp and go through a vertical loop. So we have a system which starts here. We actually don't care about this part, but let's imagine it slides down, and ends up at the bottom of the vertical loop at point A. And eventually it's going to go along the inner loop. It's going to go through point B. It's going to go through point C. And if the velocity is high enough, it's not going to leave the ramp and come back down and then sloop, keep going. Let's imagine that we know VA, so the initial velocity horizontal that E has when it starts going through the loop. What do you think will happen to the velocity at B and C? Based on what we know with respect to free fall, the effect of free fall. And we know that there is already an acceleration down. Is the velocity going to stay constant, or do you expect the velocity of the object to slow down a little bit? Slow down. Okay, good. We've all accustomed with this. So let's imagine that VA is given to us. VB will be obviously a little less, and VC will be again a little less. But it won't be zero, Kyle. Because if it's zero, what's going to happen to your object? It's going to fall down. And we just made the assumption that the velocity VA was high enough so that it will stay on the inner loop. Okay? But that's actually a great problem to work out. What is the initial velocity you need to give it here so that it stays on the ramp? That would be a great problem. But I think we need to wait until energy. So we know that the velocity will decrease, 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 and eventually on the second part, re-increase again. And since we have a nice little symmetry, the velocity that we'll have coming back will be the same as the we'll have coming in if we neglect all friction. But what I'm interested in is if we know the radius. Let's do a free body diagram on B, on A, and on C. Can you give me the two forces acting on my object at A? What are they, and what is their direction? Excellent. Weight. Thank you, Tyson. Thank you, Michael. And the normal force. The normal force is strictly vertical and up because the ground is horizontal at A. Therefore, I'm guessing that at B and C, the weight is still going to be the same. Now at B, can you give me the direction of the normal force? Excellent. Obviously, it's going to be horizontal. And since the surface is on the right side of the object, and the normal force comes from the surface and act on our object, the normal force is going to be left. And it's going to be a different normal force, different magnitude. It will also slow down and decrease. Now, following the same reasoning, what is the direction of that normal force at point C? Excellent. It will be, again, different, even lower. Good. And at the instant at which, if VA is not high enough, at the instant of which our system leaves the ramp, the normal force becomes 0, and we're back to a free fall. Good. Now, in all those cases, and A is the tricky part because it's at the instant where it starts, while B and C are a little bit more clear. What is the direction of the acceleration at B? N is 0 if the block leaves the ramp, in case VA was not high enough. Okay, can anybody, exactly, if A is not sufficient enough. Anybody can refresh the explanation for Mossman? Why is N prime towards the left on B, and why is N prime prime down on C? Perpendicular to the surface. Excellent, Dane. Thank you. That's the first half of the definition. The surface at B is on the right side, and the surface at C is up. And the second part of the definition, Dane, was that it acts on the surface, on the object. Excellent. Which means it takes out the right direction at B, and it takes out the up direction at C. Sure. Restart, Henry. We'll wait. Does that clarify, Mossman? So it all comes down to the definition of the normal force. Normal force is always perpendicular to the surface, from the surface, acting on the object. So that means if we look at a case at E, could you give me the direction of that normal force, Mossman? Is it going to be up, down, left, or right, if you follow the exact same reasoning? Hey, welcome back, Henry. Excellent. At E, it will be right. Perfect. Perfect, perfect. Okay, so now let's look at the acceleration. Obviously, from A to B to C to E, our object is going in a circle, a vertical loop. Therefore, what is the direction of the acceleration at point B? Is it to the right or to the left? Or is it up or is it down? What is the definition of the radial acceleration? If you go back to the previous board. Direction of the radial acceleration is always towards the center. Okay? Towards the center. So based on that, what is the radial direction of the acceleration at B? Excellent, it's going to be left. But you know that since the speed of the object decreases, there's going to be another one in the tangential direction. Let's not worry about this one. I only care about the radial. Okay? Perfect. What is the direction of the acceleration at c? And specifically, its radial component. Excellent. AR is down. And again, as we've seen, since the velocity magnitude changes, there is another component of the acceleration towards the left, or specifically towards the right, because the object is being slowed down. But again, we don't care about the tangential aspect for now. It's going to come back in chapter whatever, when we do revolution. Good. And obviously at A, the acceleration is up, AR. Therefore, since we know that there is an acceleration present, remember the suggestion that we had when we apply Newton's second law, if the system is being accelerated, and you happen to know the direction of this acceleration, pick one of your coordinate stem in the same direction. Hence, let's pick, say, y and x. Let's pick y and x. And let's pick y and x. So in this case, I picked my positive y always in the same direction as my AR positive. The advantage of this is that now, as I apply Newton's law, n minus w will be equal to, in the y direction, will be equal to MAR, which is m v squared over r. For B, it will be n prime is equal to MAR. So only n prime is present here. Therefore, v squared over r. This is VB, while this is VA. And at C, in the y direction, I would end up with n prime plus the weight. And that's equal to MAR, which means mvc squared over r. Okay? So always use the same trick. Pick one of your axes, you decide which one, in the direction of the acceleration. And for circular motion, the radial one is the only one we will care about. We will not care about the tangential just yet, the one that causes the magnitude to change. Okay? So keep that in mind, because we're going to revisit this problem in energy. Now let's switch to bank curve. Let's revisit, if we drive, how do we take turns? That is, if your car is here, that's the butt of my car, so my velocity is into the board. Oh, sure, wait. Let me know when you're ready. Any questions? Well, we'll wait to go to the next page. Ah, where? In which equation, you are? At B? Nothing happened to it. It's still there. N minus W is equal to mv squared over r. What do you mean, what happened to it? Can you clarify? I've only replaced the functional form of the acceleration. I haven't touched the left-hand side. So the left-hand side here is n prime prime plus. Here is only n prime, and here is only n minus W. Yep. When we do circular motion, we are only concerned right now about the radial direction, not the tangential, because we need chapter 10, 11 to do so. And that's the reason why W is not showing up in this equation, absolutely, because W is in the X. We only care about the direction along AR. Yep, perfect. Srinivas, have you figured out what happened to W? Is your question satisfied, or okay? Can I change? Okay. So let's imagine you want to take a turn. That's our car from the back. So I'm going into the page. If I want to take a left or a right, any turn that I'm going to make, if I look at this particular instant, can always be represented by a circular motion. R and R. So my circle is perpendicular to the plane and rotate about this point. That's how I'm going to go on the curve. Okay, so from the top, it looks like this. That's my circle. I'm here, and I want to go right. From Newton's point of view, if I want to take a right, obviously there must be an acceleration towards the right. Must be my AR. Since we know Newton, there gotta be a force along this direction. Can we do a free-body diagram on this little car and figure out which force is this? Can you give me a complete free-body diagram on this car? What is the first one that comes to mind? The weight and the normal force. All right, weight, normal force. So obviously none of those two is horizontal. Is there other forces down the list? Is there any tension, pulling, pushing? Is there any friction? Because obviously if we take a right, and we know we do, there gotta be a force horizontal towards the right. Which force can that be from the list? Weight is done, normal force is done. Third one on the list is any pulling or pushing. Fourth one is friction. Look, I'm going right. I'm trying to take a right, like here, right. Right, this is the center, leading from the top. This is my circle. I'm trying to take a right, like this. So this is the same motion from the top. Here, my circle is perpendicular to the whiteboard. So from the top, it looks like this. So I'm right here, and I want to take a right. If there is some pulling, Michael, then there must be some contact, right? With a force that is pulling towards the right. As you take a right with your car, is there a rope or something that appears that allows you to pull you towards the right? Cynthia mentioned there would be friction going the other way. Why the other way? And what type of friction? And Mossman, same question. Friction, I agree. What kind of friction and in which direction? Again, we're trying to take a right. Therefore, the acceleration is towards the right. Therefore, after Newton's second law, the force must be towards the right. So if you're telling me that friction is towards the left, that's not the one we're looking for, right? Otherwise, I'd be turning towards the left. Do we all agree? We're turning towards the right. Therefore, we know the acceleration is towards the right. Therefore, we must have a force going towards the right, because of Newton's second law. So, yeah, he has inertia, because he has mass. And what is that centrifugal force? Nope, only towards the right. I'm going at a constant speed into the board. I'm only concerned about taking a turn. It doesn't matter how you feel, most men. Physics is not about feelings. And I don't mean to shut you down. Because there is that whole thingy about centrifugal, centripetal. As I said earlier, don't worry about centripetal. the centrifugal. We're only going to worry about centripetal, which is by definition towards the center. So if we're trying to turn right, what is the force that must be towards the right? But what force is this? From the 4 of our list, we only know 4 forces. Centripetal force has never been mentioned. It's not a 5th force. Centripetal force doesn't exist. It's either weight, normal force, pulling, pushing, or friction. Kyle suggests pushing the same way as somebody else. So does that mean that there is somebody who pushes you for you to take a right on your car? Or are you able to do it by yourself? Thank you, Mabel. Do we all agree that friction has to be the only one? Engine is not a force. It got to be friction. Do we all agree? It's the only one left. Exactly. That's why we have the method. That's why the method is so important. So we don't create and invent a new force that we call centripetal or centrifugal or blah, blah, blah. We only know 4. It's got to be one of those 4. It is indeed friction. And the direction of friction must be towards the right. It has to be. Otherwise, we will not be going in this direction. Now, if friction is towards the right, what can possibly be the type of friction that we're dealing with? We're only concerned about looking at motion in the x direction. Either or, Michael. Answer the version you like best. Somebody suggests it has to be Fk. Or can it be Fk? For Fk to be present, there needs to be a relative motion between the car and the 4. That means the car needs to literally go towards the right. So if we plot our circle again from the top, the velocity is here, right? We just both agree that acceleration is here, and we both agree that F is here. If this is Fk, and Fk is right, what must be the direction of motion? By definition of Fk. Yeah, gotta be left. So that cannot be Fk. Right? Fk is always opposite direction of motion. Therefore, we're dealing with Fs. Excellent. Now, it is a little bit odd. Yep, we are turning right. And Fs is the one that will allow us to turn right. If you try to drive your car on ice, and your ice is a lake, you will never be able to take a right, nor left, because friction is not present. You can only take a left or a right because of friction. Now, it's a weird thing, but actually static friction is the friction that allows us to go from point A to point B. Otherwise, we won't go nowhere. I know, bizarre, but it has to be. The other way to think about it is the tires. That's what's different here. That's why we have tires. We don't slide. Because our tire, there is no relative motion between our tire and the floor. Therefore, it's got to be static. And there is no motion towards the right. Yep, that's the definition of Fk. Yep. Exactly. Here we're rolling, and we're rolling into the board, so it's even more complex. Okay? So friction is the only one that allows us to turn, and it gotta be static friction. Okay? Yep. Because if you zoom this point of contact, there is no motion. There is no relative motion between your tire and the floor. Therefore, they cannot be FK. It has to be FS. So if the wheel is turning that way, and you're going towards the left, FS has to be left. That's the one that allows you to move. Same if you look at your feet. That's your toe. For you to go that way, you're going to push that way with your toe, which means you have a force that way and a force that way. That's the force that you exert. Let's call it T. So Tx, T, Ty. For you to be able to move, there must be another force. And that's the one that allows you to move towards the left. Otherwise, you'd be paddling vomit or in mashed peas. Not going anywhere. Excellent. So we're going to revisit all this as we do rotation. Fascinating. The only point I wanted to make is when we take a turn. And I wanted to make sure that we all agree now that for us to take a turn on a horizontal surface that has no friction, ain't going to happen. We're still going to go in a straight line because there is no force that goes either left or right. So we cannot take a left, we cannot take a right turn, either or. We have to go in a straight line into the board. The only way to take a turn is if we consider friction. If you want to take a turn to the right, friction is going to pop up and go towards the right to help you out. If you want to go towards the left, friction is going to pop up and we go towards the left. Yes, Brian, excellent. Only if you burn tire, then FK is going to show up. Absolutely. So drifting means sliding, means relative motion, means FK. Yep. Excellent. I know. Excellent. So, if now I want to take a right, but I still don't have friction, what can I do? I'm here. I want to take a right, but the only force acting on me is this and this. And obviously, I cannot invent any other force. What can I do to this system so that somehow either N or W now have a component that is tilted towards the right? How can I do this? By geometry. Obviously, I cannot change the forces. There isn't anything that I can do geometrically. Well, if you add them, you're going to get 0. Excellent, Henry. The coordinate system is a good idea, but remember, a coordinate system should never influence the physics. But the surface will save us. So our usually inclined plane. Look, now if you incline your plane, what will change? Which force is going to change? Which force is suddenly going to give us a component towards the right? Excellent, yeah. N is now here. Therefore, this component of N, let's call it radial, is the one that allows us to take a right. Similarly, if I want to take a left, then I need to shift my inclined plane on the other direction. And this normal force will be the one that allows me to take a left. So if we're not dealing with friction, inclining the plane is the only way to turn. Now we do have friction, so we can use both effects now. Yep. Boats and planes are more relevant and susceptible to this. Yep, because they don't have as much static friction as we do. Excellent. So, obviously, we can take a turn if we consider no friction by just now considering an inclined plane. If your inclined plane is here, I go towards the right. If your inclined plane is like this, that will allow you to go towards the left. Perfect. And we know there is friction on top of it. So we're good. Both of them should join effort to allow us to take a left or a right. Since both already work out in every step, I'm just going to go ahead and do the friction part. Make sure you look at the frictionless. You will see that's even simpler. It depends what kind of space you have. I guess it's related to boats and planes. If you have a medium into which you could use to simulate surface friction, yeah. Yep. So if you consider space as a vacuum, then yes, you have the same problem. That's Newton's first law. If you have a particular velocity into the plane or into the board, and there is no net force acting on the horizontal direction, then you will never be able to take a turn in space. You need to have a force, either left or right, to allow you to turn. That's why they use planets. Wonderful. Let's say you're here. Let's imagine, for simplicity, we leave Earth in this direction. Let's just make life easier. If we shoot here and you escape the gravitational force of the Earth, then obviously you're going to continue at the same speed over and over and over. Let's imagine here that the net force is 0 because we're far away from the Earth. The only way we can turn is if, as we've seen, there is another force. Let's say you want to turn right. There needs to be a force here. All we have to do is wait until there is another planet. And the gravitational force from this planet is going to have a force that will be attracted towards that planet here. That's the one that we will need for us to be able to take a turn. So using the planet in our solar system will not only allow us to take turns, but also to speed up. And we'll see this in chapter 13 in more details. Okay? So mini satellites, exactly. So NASA is doing very good in saving fuel and using other planets to not only change the direction of their satellite, but also give them a new kick and a new instantaneous speed. Good. So let's analyze our bank curve. So that's for CE, future CE enemy. Question is, what is the maximum velocity that we can use for our car to take a left turn with no slipping? That is, what is the maximum velocity into the board we can have so that as we take a turn, it is safe. We don't slip, especially if there's a cliff here, like Pali Highway or Liki Liki. When you go through the tunnel, you have noticed that all the roads are curved. That's exactly for that purpose. So the curvature of the road plus friction allow us to go at, I don't know, well, I forgot what the speed limit is, whatever. So they do this calculation to be able to predict the maximum velocity, talk to the town and county, and then they make the signs. So that's what C engineers does. So let's see what they do. They just use Newton. It's a beauty and circular motion. Let's imagine I want to take a left. Alpha, that's my car, and I want to take a left here. Let's imagine I know my mass, I know my coefficient of friction, μs, μk. I know alpha, and I'm looking for Vmax. So let's do a free body diagram. Obviously, I got my weight, I got my normal force, and we just saw that if there isn't any friction, that's it. Now we're looking for Vmax. What does it tell us about the type of frictional force we're going to use? So it is obviously understood that the Vmax is the maximum velocity that we can have into the board, such that my car doesn't slip in the upward direction. Excellent. Vmax means we're dealing with Fs max. Let's continue the reasoning. Vmax is the one we're looking for so that we don't obviously slip up the ramp. What does it tell us about the direction of Fs? If we're looking for the maximum velocity into the board such that we don't slip up due to that centrifugal acceleration. Yeah, it's going to be the opposite. That's Fs max. Okay? Exactly, Michael. Tendency. So Vmax tells us that a tendency of sliding is up the ramp. Oops. Did it cut out? Oh, okay, she's back. Okay. So obviously, as you can see, if the same question was asking for Vmin, and if you're looking for the minimum velocity into the board so that the object or your car doesn't slip, obviously the tendency is to slip down. Therefore, friction will be up. So all you do is flip the direction. That's it. All right. Now that we have identified, yep, Cynthia, you back with us? Thank you, Michael. Okay, perfect. So now we have identified our three forces. Next part is to identify a current system that we'll pick. And that's where circular motion comes in. We know that we're trying to take a left. So remember, left, which means that our instantaneous circle is horizontal and perpendicular to the plane. Let me draw it. Okay? If you look at it from the top, well, I don't have a big enough board, but if you incline it a little bit, we're here, and we're going around this imaginary circle. Therefore, AR is also here. Hence, where should I pick my positive X? Along the inclined plane? Horizontal? Vertical? Excellent. That's a common mistake. People would pick X and Y parallel and perpendicular to the plane. You still can do this, but then you're going to have to project your acceleration on the other side. What if you pick your positive X to be in the same direction as your radial acceleration, which is towards the center? Then you know that the sum of forces in the X will be equal to ma, and this A is v squared over r. The acceleration along the Y is 0. Okay, so be careful about this, it's very important. If you pick X and Y perpendicular to the plane, then you're going to have to project your acceleration vector, AR, in both your X and your Y. So your X is going to pick up a cosine, and your acceleration in the Y will pick up a sine. To avoid all this, take one of your axes along the direction of the acceleration, so that your acceleration shows up entirely in one of the two equations, and the other one is 0. No. Remember, you can pick anything you want, as far as the coordinate system is concerned. You can call it Y, you can call it X, you can call it anything you want. I decided to pick it Y, but you could have done the same thing with X. The equation would be the same, right? So instead of picking this, call it Y, call it X, and then you do the sum of forces in the X. The equations, the physics, doesn't matter. Yeah. Similarly, if you're doing if say you know that the acceleration is towards the right, as you pick a coordinate system after all those forces, you're free to pick this, and it's your choice to call this Y and your choice to call this X. You could have chosen Y and X, right? The label is unimportant. It's your choice. Okay? If you don't like X and Y, you could call it radial, tangential, whatever you want. It's a free country. Coordinate system is up to you. You can always pick whatever you want. All I'm saying is, as you happen to identify the fact that your system is being accelerated in a known direction, pick any of those two axes along the same direction as the acceleration. So that as you write Newton's second law, one is going to be 0 and the other one is going to have the entire A. Then you never have to you never had to convert the acceleration in component notation. No, good question. This is an important aspect because most of the mistakes in CUM or UCM happens right here. Good. Oops, where was I? Okay. So let's finish up our free body diagram. Obviously, alpha is here, and alpha is there. Now we can project. So the two equations that you're going to get are n sine alpha plus mu Sn cosine alpha. And this is the one that is equal to MAR, which means this is the only one that is equal to V squared of R. While the Y will be n cosine alpha negative mu Sn sine alpha minus mg, and this is 0. Okay? Common mistake is what I just mentioned. Let's just do it together. So make sure that you do not do what I'm going to do, which is to skip the rule of asking ourselves, okay, which coordinate system are we going to pick? If you decided to pick the green coordinate system, then obviously what will be important? N is along Y, so we don't care. Fs max is along X, so we don't care. So we only have the angle for the weight. Therefore, the angle for the weight must be this one. If you project along the X and along the Y, you're going to have mu Sn for X plus mg sine alpha, and in the Y, n minus mg cosine alpha. What you should not do is do this. That's the common mistake. Okay? In this green current system, the acceleration, which is horizontal, obviously has a y and an x. Your angle alpha will be here. Nope, it will be here. Oh, let me redraw it. So if this is A, then you're going to have AY and AX. Okay? So if we call this beta, which is 90 minus alpha, then AX is going to be sine of beta, and this one is not going to be 0, it's going to be m v squared over r cosine beta. Okay? So this is what you will get if you don't pick one of your axes along the acceleration. Okay? So be careful of this. When you go in a circle, as you pick your coordinate system, make sure that you identify where your circle is, your instantaneous circle, so that you're very clear about where AR direction is. Once you have identified where AR is, bang, you pick either your positive X or your positive Y in that direction. And this allows you to have one zero and one full acceleration. If you don't do this, it's fine too. But then remember, same technique and consequences as we have encountered before, then you have to convert your acceleration vector also into your coordinate system, which is more work and more susceptible to making mistakes. Okay? So make sure that you practice this problem with Vmax, then do Vmin, then take out friction, redo Vmax, and redo Vmin. Those are very easy, straightforward application of circular motion. Okay? Questions on this? That was with friction. I said without friction. Redo the same one with Vmin, then redo the same one without friction, both Vmax and Vmin. So 4 cases. Because we just did friction, right? So obviously without friction, same thing except those 2 terms will be 0, right? So the without friction case should be easier. And again, they both worked out in the core subsite. No, remember, I always suggest you all to do variation of what we do. I did it with vectors, I did it with kinematics, and I keep doing this as we do Newton. Whenever we do one typical problem, I always suggest, okay, do this variation with this and this and this. It's up to you. I'm not going to collect them. They're not new homework. I cannot change the syllabus. Is that what you're referring to, Jamie? This is not extra homework that I'm asking you to do. I'm only suggesting that this is something that you should strongly consider, because usually when I give those hints, you know, it's going to show up on the test. So, you know, it's just up to you. Exactly. Just different type of practice on similar type of problem to deepen your understanding. Excellent. Yep. Yep, yep. Exactly. Exactly. You got it. You got it. Perfect. Let's take a quick break and let's go over conceptual drag force. It's already on the lecture, so I'm not going to duplicate what's in the lecture. I just want to go over it conceptually and suggest that you work out, as in this particular case, a new version of it, since one version is on the web. Okay, and then we'll move to the chapter of energy. But before we do this, I need to revisit vectors. So I'm going to go back to the schedule page and look at the section of chapter 2 on vectors that now we need to revisit to be able to be ready for energy and work. It's going to be dealing with projection of vector along any direction, dot and cross products. All right, quick break. Let me release the boards. Whoops. So you can look at it over the break if needed. Okay, so before we start energy, we need to revisit the tools for us to be able to survive this. Therefore, we need to go back to the first chapter on vectors and go over the section that we skipped so far, which were the dot product and the cross product. Let's start with the easiest one. If you have a vector A that you want to cross, wait, we can do the cross later. I'm sorry, let's do the dot product. If you have a vector A that you want to dot with a vector B, when you deal with vectors, it's different than dealing with scalars. We know that there is 4 operators for scalars: addition, subtraction, division, multiplication. 4. When you deal with vectors, you still have 4, but they're a little bit different. You keep the addition. We know how to add 2 vectors. We keep the subtraction. We know how to minus 2 vectors. It's just a flip in direction, no problem. But we cannot divide 2 vectors. And we cannot multiply 2 vectors. So we're going to lose the division operator. And the multiplication operator is going to disappear and morph into 2 types of operator: a cross product and a dot product. So there are 2 different types of quote-unquote multiplying vectors. So let's go over one of the 2, the dot product. When we get to rotation, we're going to go over the last one, which is the cross product. So dot product. Weird thing about this is that we end up with a scalar. That's a weird little thing. You start with 2 vectors, you dot them, you lose the property of vector. You end up with a scalar. Very bizarre. 2 properties. If A dot B equals 0, and it's the 0 vector, it means that A is perpendicular to B. And the second property is if A and B end up with a maximum value, then A is parallel to B. If they're both parallel in the same direction, the value is maximum and positive. If A and B are parallel to one another, but they have opposite direction, same maximum value, but it would have a negative sign. The reason for this is that you can always calculate the dot product by taking magnitude of A times magnitude of B times the cosine between the two. But I'm going to move away from this definition because that's something we will never ever use. Instead, I want to be able to take two dot products between two vectors if each of them are already expressed in component notation, because we know how to do this. Because the disadvantage of AB cosine alpha is that we need to know the magnitude of A, we need to know the magnitude of B, and we need to know the angle alpha, which is between A and B. And that's usually not the angle that we know. If we know this, we know the angle between A and our X or Y axis, and if we have B in component notation, we know the angle between B and either our X or Y axis. We don't have to go ahead and try to figure out, based on the orientation of A and B, what is that stupid angle between the two. It's a waste of time. So I'm going to neglect and ignore this definition. Instead, I'm just going to use this one. Distributive rule. A dot B. Easy. AXI dot BXI plus AXI dot BYJ plus AYJ dot BXI plus AYJ dot BXI BYJ. Okay, so distributivity operator, property can be assigned to both scalar and vector. Now, for each term, I see two scalars and two vectors. So let's gather all the scalars together. AX times BX, this is still multiplication operator, but then I have to do I dot I. Next one, AX BY, multiply them together. Sorry, I just got kicked out. But then I'm back again. Is everybody? Oh, so I guess it was just me. Okay. Oh, everybody does. Oh, okay. Okay, is everybody back? Okay, perfect. So, now let's identify. Hey, I just lost my board too. Oh, yep, Henry, you're right. So what we're saying is I'm going to group all the terms, put the scalars together, and then keep the vectors together. And then the third term, same thing, AYBX, and then J dot I. And then for the last one, I will multiply the two scalars together with the multiplication operator. That doesn't change. But then I have to take the dot product of J with J. Okay. Oh, I didn't get kicked out that time. Oh. Am I a squirrel just for you, Henry, or for everybody? Ah, just for you, Henry, sorry. You know what may fix your problem, Henry, is if, I'm guessing you're on Wi-Fi. If you're on Wi-Fi, try connect directly to a router. That will fix this. Oh, well, bummer. Then I have no idea. So is everybody hearing a scroll? Should I be the one disconnecting and reconnecting? Oh, Cynthia is okay. Yeah. Okay, so it seems to be, yeah, I had a hard time too, Michael. I have to go it 3 times. Yeah, I hear you, Jimmy. Okay, hopefully they will fix up their server or something. I guess so, yeah. So, let's go back to our little sheep. Based on the 2 properties of the dot product. If A is perpendicular to B. No, you should be able to re-click on that meeting.collab. Henry, sometimes. When you first click, it downloads a file called meeting.collab. If you re-click on this, you should be fine. You shouldn't have to read on a new one. Oh. Yeah, sometimes like I never do. I always reconnect with the same one. Try that first, because it may go faster. Ah, okay, okay. So if it keeps failing, then you have to re-download a new one. Huh, bummer. Okay, so how am I going to deal with I.j and j.i? Knowing the property of the dot product. If 2 vectors are perpendicular to one another, their dot product is 0. Can this be used to calculate the dot product between I and j? I, by convention, is the unit vector along the x-axis. J is the unit vector along the y-axis. Oh, Carl, you're back. Good. So, how can you use this exactly? The commute, same. So that tells us that every time you want to take a dot product, the only term that will survive are the like term. All the x multiplied together, all the j's multiplied together. Because what is the result of I.I? Remembering that I is a unit vector. Now we can use this. If you replace A by I and B by I.I will be magnitude of I times magnitude of I times the angle between I and I. Yeah. 1. Exactly. That's the beauty of unit vectors. So I.I is 1, J.J is 1. Therefore, the result is AXBX plus AYBY. So when you take the dot product between 2 vectors that are in 1D, 2D, 3D, 4D, 5D, 100D, and you want to dot them, all you have to do is multiply all the x components together, then add the multiplication of all the y components together, and add all the multiplication of the z if you have them, etc., etc., etc. Those are the only ones that will survive. Super easy. Okay? So that's how we calculate dot product in component notation. Cross product will be very similar, but a little bit different. But we'll see this as we start rotation. So make sure that you master dot product practice, make up your own problem, pick up 2 vectors, dot them. Send it to me if you want me to check. What I want to do is I want to use this to go 1 step further, which is to help us prepare for 3D problems. Yep, Michael. Right here. So, in 2D, whenever you want to project and express a vector A in component notation, if you only have 2 dimensions, then it's easy. You only need the angle between your vector and either x or y. Because then we use trig. Adjacent, cosine, opposite side. No problem. Now, what about if you're in 3D? And your vector A is here. Yep. How would you apply trig? How would you express the AX component, the AY component, and the AZ component? Do you need more than one angle? Or can you get away with one? So, if we pick the angle between A and X, how are you going to calculate AY? And how are you going to calculate AZ? Sure, this one will allow you to get the X component, because it's between your vector and the x-axis, theta. So this case is going to be a sine, or a cosine, proportional to a cosine. But what about AY and AZ? And pyramid have how many angles? 3. Absolutely. You need one between your vector and y, and you need one between your vector and z. And you can use trig on both of those dimensions. So you need 3 angles in 3D. A total nightmare. Those are called cosine angles, or they're related to it. You're going to see this in C270. But again, in that class, you're going to view them once and forget about them as soon as possible. Instead, we're going to rely on calculus, vector analysis, or dot product. This will help us survive 3D. So in 2D now, you're going to have 2 choices. Either use trig, or you're going to be able to use the dot product. So, application of the dot product. If we go back to 2D, my claim is that if you have a vector A, and I would like to figure out what we used to call AX, and AY, you can get it through another way. Instead of going through angles, sine and cosine, AX, which is what I will call the component of A parallel to the x-axis, is going to be vector A dot I times I. This is where the dot product shows up. So I'm going to take my vector in component notation. I'm going to dot it with I. That will give me a scalar. And I'm going to multiply this scalar by I again, and this will give me AX. Similarly, AY will be A parallel to the y-axis, and is equal to vector A dot J. Okay, so that's a new definition that we are learning. We can decompose any vector in any direction using a dot product. Let's pick a case that is a chicken and egg case. Let's imagine that we know or given A such as A is equal to 2I plus J. Or let's say 3I plus 2J. Obviously, what is AX? AX is 3I. AY is 2J. We knew that right off the bat. Okay? No problem. Let's make sure we get the same value using this definition. Let's calculate A dot I. Can anybody give me the results of A dot I? Using the property of the dot product we just saw. If 2 vectors are parallel to one another, it is the product of those 2 vectors entirely. If they're perpendicular, then it's going to be equal to 0. A dot I will be 3I plus 2J dot I. What is the result of this? Use the distributive rule like we did. 3I dot I plus 2J dot I. Yep, almost. And what is I squared? Which is I dot I? 1. Excellent. So this is just 1 times 3. Do we all agree? Remember, it's a scalar. Dot product is a scalar. Dot product is a scalar. Dot product is a scalar. Excellent. Okay? Similarly, A dot J will give me what? Using the same technique? Excellent. 2. Let's multiply this by I again and multiply this by J again to complete my formula. Bing. Bing. So sure enough, it's the same. Okay? So for 2D case, it's trivial because we already know the answer. But this confirms that this new formula will allow us now to project any vector in any direction without having to use cosine theta, sine theta, cosine blah blah, sin blah blah, no more trick. The beauty of this is this can be extended to any direction. So I'm going to use the letter E to denote the unit vector along any direction. Oh, excellent question, Michael. In 3D, you will never have the case of I dot I dot I, right? Because you're only using the distributed once. You're going to end up with I dot J, I dot I dot K, and then J dot I, J dot J, J dot K, and then K dot I, K dot J, K dot K. Hence, in 3D, the only one that will survive are the I dot I, J dot J, and K dot K. All the cross term, I dot J, I dot K, J dot I, J dot K, K dot I, and K dot J will be all 0. So even in 3D, you only take the dot product once, right? Try it. Pick 2, 1, 2, 3, and then use the exact same rule. You will see that the only one that will survive is this times this, plus this times this, plus this times this. Excellent. Good question. So this is the one we're going to be using. This will be the definition to be able to project a vector in any direction. E being a standard name to represent any direction. So we're not restricted to X and Y anymore. That's the beauty of this. And we're not restricted to 2D. We can do it in 3D, 4D, 5D, 10D. Let's do an example. If I have a vector A, let's pick the same one. 3 and 2. And I want to project the vector A along the direction where it is here. Let's say 45. Let's represent this graphically. What do I really want? Imagine that this line 45 used to be your X or Y axis. If I want to figure out the component of A parallel to this yellow line, then I'm going to start along the yellow line and go perpendicular to it, like we did before with X and Y. This is what I call a parallel. This is what I called a perpendicular to my line. I want to express and figure out this vector first. Of course, this vector will have 2 components. AX, A parallel X, and A parallel Y. Let's get those, and then we can deduce a perpendicular. If we trust the definition that says A parallel, by definition, is vector A dot E. That gives me a scalar times E again. Then really, I need to know A, and I need to know E. E being the unit vector along the direction about which I want to convert the vector. Therefore, E is along this direction. Obviously, you can pick this E, or you could pick this E. They're both along the direction L, which has no direction. So either or. E won't matter because E shows up twice. Therefore, if you pick this one versus this one, the only difference between those two is a negative sign. The negative sign will cancel out. So it doesn't matter which E you pick. Let's imagine I'm going to pick this one. Can you express E in component notation? if the direction of the line is 45. Let me give you a hint. If this is 45, I'm looking for the unit vector along this direction here. Unit vector is a unit vector, right? Therefore, its length is 1. So this is 1. And I want the x and the y component, or the y and the x component. Excellent. Yeah, it's just a unit circle. Perfect. E will be negative sine of 45 and positive cosine. Perfect. So that's the trivial case. So in this case, it would be sine 45 and negative cosine 45. Perfect. That's it. That's all we're going to do. Because now it's just plug and chug. Let's do this. Can you give me the dot product of A times E? I'm sorry, not times. A dot E. Remember, the only term that will survive are I dot I and J dot J. Can you give me a number that represents the dot product between this vector and this vector? We're doing the parentheses. Can you give me the sum of two products? Because remember, the only one that will survive are the i's multiplied together, added by the j's multiplied together. Yeah, excellent. Which end up being square root of 2 over 2. Perfect. And we're going to multiply it by E again. Therefore, our final vector, A parallel, is nothing else but square root of 2 over 2 times sine 45 and square root of 2 over 2 times cosine 45. This is this vector expressed in complementation. This indeed is positive and this indeed is negative, as predicted, if I use my standard x and y. Okay? So this is quite powerful. Now you can decompose a vector into two vectors that are still perpendicular to one another, but you don't have to be restricted to x and y. Oh, because this is square root of 2 over 2, right? Multiplied by the magnitude again. Yeah? Perfect. Now we could do the same thing with A perpendicular. A perpendicular would be vector A dot E prime. And E prime will be unit vector along this direction. And you will learn in Calc 3 how to figure that out. In science, we decided, too much work. We know that A is equal to A parallel plus A perpendicular, right? This is A. This is A. We now just calculated A parallel, therefore we know this. So let's just solve for A perpendicular by taking A minus A parallel. Bang! Easier, faster, one line. So try both. If you're in Calc 3, make sure you use the tools of Calc 3 to figure out E prime. Do the same formula, you'll get to an answer. And then use that trick, which takes only one more line, and convince yourself that you have the same answer. Okay? So usually, we would be interested in A parallel. Okay? Now that's for the case where we would like to project the vector along a direction that is given to us in terms of an angle. But let's say now you want to do 3D. This is my vector A. Let's add a three-dimensional to it. 1, 1, 1. And my line, say, goes like this. It goes through 2 points. B, which is -1, 1, -1. And C, which is 2, -1, So obviously, my projection is something, if I move my vector so they start with a line, there's going to be something here. That's my A parallel. But it's in 3D. So it's pretty gnarly to try to figure out in which direction it is. If we use that recipe, no problem. First, let's write down the recipe. A parallel is equal to A dot E times E again. This time, the line is not given to us by 3 angles, because it's 3D, but instead, it goes through 2 points that are known. Aha! And we're interested in the unit vector along that line. So could you relate that unit vector E that we're looking for with something else that we've done before? What is this vector E equal to? If you know that the line goes through 2 points, you've used it when we did problem in equilibrium. Specifically, you've used it in E7. When you did problem E7, you use the exact same case. How would you calculate unit vector E? If you know that B and C are in the same direction. It has to do with unit vector's definition that you have employed when you did and completed problem E7. Go back to your notes. This problem should have been done long time ago, so you have it. What trick did you use? Give you a hint. What is the relationship between position vector BC and the vector E that we're looking for? Do they have something in common? By definition of a unit vector, which you have on your note as well. Can you draw the unit vector of position BC? As you draw it, can you find the relationship between this unit vector and the one that we're after? Yep. Almost, Kyle. There is no such a thing as EC or EB, but you're almost there. If you have 2 points, B and C, you can draw the position vector BC, right? Can you also draw the unit vector EBC? And if you do, can you now identify the relationship between the unit vector of position vector BC and the vector E that we're looking for? Correct. That's the unit vector EBC. What is the relationship between the unit vector of EBC and E, which is the one that we're looking for? Excellent. That's it. So it goes back to unit vector. It goes back to the definition of unit vector. This E is nothing else but EBC, which we know how to do. Therefore, there is nothing new under the trees. We know B, we know C. Therefore, BC over BC is entirely known. That's the definition of EBC. Hence, position vector will give us 2 minus 1, that's 3. Minus 1, minus 1, 0. Oops, minus 2. And then 2 minus minus 1 is 3. That's position vector BC, right? Divided by its own magnitude, 9 plus 4 plus 9. That's my EBC. This is the unit vector that I will use right here and right here. So now it's a piece of cake. As we take the dot product, it's going to be this times the x component. 1 times 3 divided by, what is that, 18 plus 22. plus 1 times negative 2 divided by square root of 22 again, plus 1 times 3 divided by 22. That's the dot product. And we're going to multiply this by the unit vector again. And that's it. This is a parallel. That's a stupid vector. That's the length of the vector from here to here, and that's the direction of the vector. So you can literally now project any vector that you have in component notation along any direction. And you don't have to be restricted by X, Y, Z, or whatever. Okay? So note, as I mentioned earlier, you could take either E or E prime. Doesn't matter. If you take E prime, you're not going to deal with position vector BC. You're going to deal with position vector CB. Yeah, feel free to use the calculator, get rid of that stupid square root. Only 22 will survive. Excellent. Yeah, because it shows up in 2 places. Good. So again, if you had chosen this unit vector, then you would have worked with BC, and therefore, CB, and therefore ECB. But again, the relationship between ECB and EBC is just a negative sign. Since you're going to use it twice, it will disappear anyway, and the answer should be the same. Okay? Which implies that it's perfectly fine to have a dot product that is negative. A dot product can be negative. It means that both vectors are in opposite direction. So if you get a negative number here, it's fine. It's fine, it's fine. You're just going to flip the direction of this little bugger. That's all. So you can have both situations, positive or negative. If you got 0 here, that means that those 2 vectors are perpendicular from one another. Then a parallel is just 0. Okay? So there's plenty problems of that type under the vector part E. Wait, is it part E or part D? That product is part E. So make sure you do them all. Part 1, 2, 3, 4, 5, 6. And if you haven't watched the video by then, please do so. Okay? And as we start rotation, then we're going to go to the last part, which is section D, cross products. But we don't have to worry about it just yet. Okay? So now we're perfect to do energy. There is 5 of them. They're under the section E page. So if you click on vectors, if you click on schedule, you will see the math requirement for this chapter, which is vector C, section C and E. So you have a link on the schedule page. But now I realize it shouldn't be C and E, it should be just E. C, we already did it. Oh yeah, no, so that's for Newton and equilibrium. We did that already. Okay, so only part E. And again, as we start rotation, then we're going to revisit section D, which will be useful for cross products. Perfect. So again, if 6 problems is not enough for you to master this, create some more. Pick a vector, pick a direction, 2D, 3D, try it out, and take a picture, send it to me so I can double check. So you can make up any problem you want on this type. 1, 2, 3, 4, 5, 6 is posted. You can go down to all the way to 10. Create new problems in 3D, 4D. You should be able to handle any direction now. Always the same principle. This will come back with a rare violence in C270. So if you're thinking of going C or ME, and as the class you're going to take next semester, F dot E times E again is going to be your best buddy, because most of the problems are 3D in C270. So that's the only way you can rely on decomposing a vector in component notation. You won't be able to use trig anymore. Perfect. So, energy. What do you know about energy? Can you summarize me all the lectures and all those concepts and videos and the whole book chapter in one line? Wrong line. That is true too. This is what we would call a potential type of energy, JV. But go broader. What is interesting about energy in these two chapters? What is the main idea? One main idea. And I'm sure you've heard in high school, it's so common. And it doesn't have to do anything with MC squared just yet. Excellent, Mosman. Thank you. In other words, can you say that in layman's word? Rather than being very specific and analytical. Can you express this with one sentence? So that we get a feel of what's going on. Sure, energy can be decomposed in terms of potential and kinetic. And if you add all the potential and all the kinetic at some point, and you do the same at some later point, they are going to be the same. Can we rephrase this in one sentence? It is also a property of the equation you wrote above. But it's still technicalities. I just want a main idea. What is the main idea of energy? Specifically, energy happens to be conserved. What does that mean? Can you explain to me in one sentence? Excellent. Thank you, Mallory. Yep. Energy cannot be destroyed nor created. Which means that if you sum all the energy at state 1, and you calculate the sum of all possible energy, potential, kinetic, blah, 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 in state 2, they are the same. That's it. That's the lecture for chapter blah blah and blah blah. That's pretty much it. Chapter 7 and chapter 8. That's it. Now energy will flow as we go into each. This really is the sum of all little energies. At position 2 and position 1. So energy will flow from one to the other, or rather from this type to this type, this type to this type. So for example, if you have a KE here, kinetic energy and a potential at position 1, and again we have a different kinetic and different potential, we know the sum is always, say, 5. Therefore here it could be 3, here it could be 2. Later on, this could be 1, this could be 4. So energy flew from 3 into 4. Okay, so 2 of them left the KE and went to feed the PE. Okay, so that's how energy can change form. Yep, they just oscillate between different states. Yep. Absolutely, Osman. So energy, as Adrian suggests, can always transform itself from one type to another, kinetic to potential, depending on the process, which is right here. But the sum is always the same. So that's what we call energy conservation law. The whole 2 chapters are based on this. It's a one-line equation. And this will be the only equation that we will use to solve every problem. Therefore, technically, it's a one-line problem. Can it get easier than that? Now, of course, as we can see, the line is going to demand a serious method and a lot of steps. That's okay. We'll go through the method as we always do, so that as we revisit energy during rotation, then we can handle the much higher complexity as the one we've seen so far. Same for Newton. We've done all the B stuff. When we do rotation, we're going to take Newton, take energy, combine them into a new set of problems, and the complexity will be much higher. But if we know the method for Newton now, and we know the Newton for energy now, when we get to that stage, we can handle it. If we don't master the method for Newton energy by the time we get to rotation, we might as well drop the class. Michael asked, well, when we start to apply energy, don't say where the initial energy went into. Don't we say where the initial energy went into? So what do you mean, Michael? Like, for example, in this case, we start with 3 of kinetic, 2 of potential, and at the end we have 1 on kinetic and 4 on potential. So based on those numbers, we're able to say that 2 units of energy that was in kinetic transformed itself into potential, so that 2 became 4. Did I answer the question, or am I missing the whole? So we know how it transforms itself. There's no such a thing as energy going to acceleration, because acceleration is a kinematic variable. However, there is something that links energy with friction. Yes. Okay. So if you are thinking about internal process, such as burning, this is beyond the scope of the class. This is what you will learn in thermodynamics. And you will learn that through the process of having an internal work done. So as you change the form of energy from one type to the other, you need a process, like burning. This process will cause energy to escape your system. So you will see this, but you will see this in 300, 400 level. In this class, we would assume that the conversion of one type of energy into the other is 100% efficiency. Excellent question. So we won't lose energy during that transformation. We don't actually care how it happens. Good. Is that what you had in mind? Perfect. However, when you mention that line of energy that is in friction, look, that's thermodynamics and the cutter of this class. So this is something you will see if you become an ME. You have a whole year. And thermodynamics is something you should have seen in chemistry class, which is the reason why physicists dropped it from 170 last summer. Which makes our life easier. So we have less to cover. Because they assume that you've seen thermodynamics, or at least the basics in chemistry. So you'll be able to handle the 1 year of thermal as you become CEME and the 1 semester in physics. So I just want to go back to the line of energy that is in friction that Michael suggested. There are some forces that we call conservative, and there are some forces that we call non-conservative. I don't know where they picked that word, but I like to believe that they meant to be energy. Which means that if you're dealing with conservative forces, you don't lose energy. The energy is being transformed and stays in the equation. But if you introduce non-conservative forces, such as friction, then you start with some energy and you end up with 0 energy. So somehow we have a leak. For instance, if we associate kinetic energy with motion, that is, every time you have motion, you have kinetic energy. Let's imagine we start on the horizontal plane and you have high velocity. Our object is going towards the right. Obviously, at this stage, it has some kinetic energy. Okay? Let's neglect potential for now, only consider kinetic. If there is friction, what will happen to the velocity right here? Is it going to stay the same? Is it going to get bigger? Or is it going to get smaller? It's obviously going to decrease, yeah? If you wait long enough, what will have to occur about the velocity? If you throw an object on the floor, let it slide. Exactly. It will be 0. Therefore, if we believe this, that every time there is a motion, there is kinetic energy. If there is no motion, then kinetic energy is 0 here. Well, it is not 0 here. So if we add all the type of energy, which is only KE here, we get, I don't know, 3. I'm going to forget the units just yet. And here we add the type of energy, and we have 0. Obviously, this cannot be right. Right? Either we need to add a term here, which is positive, or we need to add a term here, which is negative. And it has to be equal to 3. So either you put -3 here, or we put positive 3 here, so that this is still valid. This is the type of energy that will escape your system due to non-conservative forces such as friction. So for us to be able to still use that equation, that E, sum of all the E at one state is equal to sum of all the E's at another state, is to take care of that extra term in case we have friction. By convention, we're going to add it towards the left, so that it's consistent with the definition of work. This will take care of any forces that may escape through non-conservative forces. Now this is true for every system, and that's the one we're going to use. So as you can see, energy and work are exactly the same concept in physics. So we have to read about work. You have to read about work, watch the lectures, read carefully about work in your book in order for you to understand the new definition of work, which is quite different from the layman definition that we know of, that we'll be used to. Okay? This work will be defined as a dot product. That's where the dot product is going to come back. That's where calculus 2 is going to come back. Okay? So that's where we're heading. Before we get there, we still have 3 minutes. Let's just define those terms. We mentioned KE, and who was this? And Mossman mentioned PE. Those are the 2 types of energy that we're going to see. The E is equal to mc squared falls within this category, but you will see this in Physics 274. For us, we're going to see 2 PE. PE due to gravity, PE due to a spring, and KE only 1. They're all about translation. When we get to rotation, we're going to double the number of terms. We're going to have 1 K for translation, 1 K for rotation. So we're going to keep increasing the number of terms. But for now, only 3 types. This, as we mentioned, is about motion. This is about height. And when I say height, I mean vertical height. And this is about a spring. Spring, 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 spring. The energy stored into a spring. So we're going to see those 3 types. So energy will be able to flow from one to the other with 100% efficiency. We won't care about internal engine, for example, where we lose energy through heat and through friction. So, definition that you will see as you start looking at the video is KE will be defined as 1/2 mv squared. PE due to gravity will be mgh, and PES due to the spring will be 1/2 px squared. So this will give you the opportunity to learn about the spring as well, which also has a force. So we'll see both. So all those are definition of different types of energy. We add all those energies together, therefore they better have the same units. Let's check the first 2. Convince yourself that they have the same units. Let's plug units for each of those variables and make sure you have the same. What is the units for M? Mass. Kilogram. What is the units for V? Velocity. Meters per second. And it's squared. So this must be units for energy, kinetic energy. Better be the same for PE. Let's double check. This M is the mass, again, kilogram. G, hey, our favorite G. Remember? That shows up in the weight, always positive, 9.81. The units for this is meter per second squared, because it's the acceleration due to gravity. Meter per second squared. And h is the vertical height, therefore meter again. This is what we're going to define as joules. Okay, so joule is going to be our unit for energy. Okay, and we will do that later when we see the spring. I also mentioned that we're going to add a bunch of PE with a bunch of KE at two different states, but to figure out and handle the case where energy escapes your system, we need to add another term, and we're going to call this work. Therefore, those two they have the same units. Let's check. This is defined as the force dot dr, displacement. This must have the same units of kilogram meter squared per second squared. Let's check. What is the units of force? Newton. Now, can you give me the SI version of Newton? Newton is really, we went over this when we first, excellent. It was defined as kilogram meter per second squared. Excellent, Michael. Almost perfect. What is the units of R? It's a displacement. Change of position. Therefore, it's meter. Look, same. So work, energy, same thing. One creates the other. So it's by acting with a force along a particular distance that we will be able to either add energy into a system or take out energy out of the system through this term. Okay? So if it's a case of friction, obviously this would be negative and energy will be lost from 1 to 2. Yep. We can write it that way as well. Newton meter is the same as joule. And same as kilogram meter squared per second squared. Either one. Absolutely. Good. So please read about chapter 7 and chapter 8. The FAQ is very, very important. So make sure you spend some time on this. Almost as important as the FAQ for Newton. So make sure that after you watch all the lectures, watch the corresponding book, read the corresponding book section, you go back to this FAQ. There's only one little mistake in there, which I've never corrected. If you find it, please let me know. Oh no, I did get out. Okay, good. I hope I did. Hopefully it's not there anymore in words. Now, in the FAQ, Jimmy, I remember writing something like sum of the work is equal to 0, but I don't see it, so that's good. I must have taken it out. Perfect. It won't matter for the solving problems. All right, perfect. So this is your next test. Next task is to read the lectures on chapter 7, chapter 8. There is several. A1, A2. Work energy theorem, one on springs, so this will allow you to discover springs, and friction. The part D is optional. And then after that, make sure you look at and read the corresponding section of the book. The book is very good on those two chapters as well. And then read the FAQ. Okay, those are very important relationships. Perfect. 7, Pau, let's go home. I just want to keep the WI real fast because I only know of one person who started their homework, but I haven't heard of anybody else. So if you're not in a WI, feel free to go. If you like to stay during office hours, stay until 7:20, roughly. If you're in the WI, please stay and let me know how the second homework is going. I will be with grading your first homework within the next couple of days. All right, quick break. Let's meet again in 10 minutes.